We're talking about optimization today. So we've talked about the vanilla gradient descent. We're going to see some other alternatives today and try to understand the intuition for them and how they work. As far as business, we have readings due this Saturday, labs 3 and 4 due this Saturday. However, we've had it seems like all of our TAs have had things come up displacing their office hours this week. So how would you guys feel about bumping lab 4 next Saturday? All right, okay, we're gonna do that, and then we're going to bump all subsequent labs as well. So we have an extra week for that. Okay. All right. So last time we talked about pixel translation or image segmentation. Image segmentation is specifically the case of pixel translation, where we are going from more information to specific classes. And we discussed the deep UNet architecture as well as transpose convolutions. Any questions on those concepts? Yeah, Brendan.
Yeah. So when we're doing the UNet, do we have to continue stating different variables that aren't the ones that we're using later?
No. The question was whether you need to save any variables other than the variables that are being copied over and concatenated, and the answer is no. Okay, so just take a couple minutes, turn to your neighbor, and try to answer these 3 questions. How does dense prediction or pixel-to-pixel mapping differ from classification? How does the UNet architecture work, and why are state connections useful?
So, prediction takes a picture, takes a whole bunch of input, and gets one resolution. Whereas pixel-to-pixel is based on the picture.
You have a lot of different layers of features that are later abstractly thinking about it. You can pull from multiple processing. Basically, you can pass variables. Which, I mean, that reflects real world programs, but it's definitely throwing the kitchen sink at it and saying, take things, which, like, that can work. Use all variables are in scope. Use whatever you want. I guess that's why I'm.
All right, so we've got 1 more minute.
I understand what but it's like, so we're getting the more general now, and then we're using the build backups into the just translate abstract feature A into it's with work maybe that train.
All right, so yeah, let's see what did you come to as far as answers to this first question. How is pixel-to-pixel mapping different from classification? Yeah.
You're basically classifying every pixel.
Exactly. Classifying every pixel instead of classifying the entire image. Or in some cases, that's a case of image segmentation. If we're doing image generation, then rather than classifying every pixel, we're generating every pixel. Yeah, and then I have someone answer these other 2 questions. How does the UNet architecture work, and why are state connections useful? Yeah. Yeah, that's a great description of the unit architecture. So then how about this part about why those skip connections are useful? Yeah, same thing. Yeah. Totally. Yeah. Combining the coarse grained features with the abstract features. Totally. And we also saw in one of the later slides last lecture how adding those skip connections also smooths the loss landscape quite a bit. And you can imagine that that's possibly because gradients have a shorter path to travel from the loss back to the weights that are being updated at the earliest layers of the network. Yeah. Yeah, so the question is about concatenation. So do you understand which of the dimensions we are concatenating? Are we concatenating them like one image stacked on top of another, or one image next to each other, next to the other, or stacking along the channel dimension? So yeah, so we're stacking on the channel dimension. And so basically you can think of that as we're just adding, like in the same way that we have R, G, and V channels in our original image, we have additional channels of features for each position in the grid. And we're concatenating those. Does that make sense? Yeah, and then also I should point this out, this is important for lab 4. The unit paper starts with images that I think are 572 by 572, and they shrink slightly in size with each convolutional layer, and then they end up copying and cropping a smaller version of the earliest activations to the end of the network. And you can imagine that there's probably some information loss there. But I'll tell you that if you use padding, so in the lab, your images are 512 by 512. If you use padding at every layer, your outputs will have the exact same spatial dimensions as your inputs. And so you'll be able to concatenate without cropping. So that's probably what you want to do. Okay, so today we're going to be talking about non-batch normalization, gradient descent, and all of its variants. So as a review, we have a task. For example, this is a new task that we haven't seen before. This is called object detection, where our job is to draw a bounding box around a car. And to do that, we take as input an image and predict an X, Y, W, and H values, where X and Y correspond to the top left corner of that bounding box, and width and height correspond to the size of it. And so we define a loss function, which is the mean squared error between each of these predicted values and the true values of the bounding box. And we produce a loss, and then we take the gradient of the loss with respect to our network parameters and use that to update our network parameters. And so the optimization part is, how do we use our gradients to update our parameters? You've probably been using in the lab so far either ATOM or SGD, stochastic gradient descent, without really knowing how those work. So today the goal is to understand how those work and why we use those algorithms. So I guess just to introduce some terminology, we are trying in deep learning, we are trying to minimize the loss function, and we call it the minimum of a function, the minimum, a maximum, and then a point that is a maximum in one dimension and a minimum in another dimension. We will call that a saddle point. That image of a saddle point is somewhat deceptive. Let's see. we'll see a better picture of a saddle point later. Okay. So in deep learning, this is an example cross-section of a loss landscape with some possible minima. So here we have one, what's called a local minimum. It's not the minimum of the entire function, but it is a point at which there's a certain range on either side at which it is the minimum. And then we have two other local minima. This one's, the one on the left is slightly lower than the one in the middle. But if we can get to the one in the middle, we're probably fine with that because the loss is almost exactly the same. So then another term, we have curvature. So all of these functions have the same slope at this point. However, the curvature of the at this point is it's the second derivative at that point, which describes basically how fast the slope is changing. And the curvature is something that's going to have a pretty big factor in why just vanilla gradient descent does not work. This I think is a better picture of a saddle point, and I think it describes why we call it a saddle point, where we have this is a function over two variables, and it achieves a minimum with respect to x1 at x1 equals 0, but at x2 equals 0, it achieves a maximum. So at the point 0, 0, it's called a saddle point because it's a minimum with respect to x1 and a maximum with respect to x2. And it turns out actually that in gradient descent, it's really easy to get stuck in saddle points. When you have millions and millions of parameters, it's very rare that you are at an actual local minimum. It's more likely that you are at some sort of a saddle point where you're at a minimum with respect to a lot of your variables, but at a maximum with respect to a lot of others. And that can slope. And so when we say getting stuck in local minima, often it's actually getting stuck in saddle points. So as far as optimization algorithms, we have different algorithms that work in different ways, but even starting with the same initialization, the same initial points, can take drastically different amounts of time to arrive at the desired global minimum. And so, yeah, take a look at this for a couple of seconds and talk with your neighbor about what you notice happening in these different colored balls, so to speak, that we have rolling down the scale.
So I'm also
All right, yeah, what are some things that you notice about the patterns that these different balls take rolling down to this way? Yeah. Yeah, so you pointed out that it looks like the momentum is starting with a shove. And also to help understand kind of what we're looking at here, the color of these curves indicates their elevation, and then their proximity to each other. The proximity of these lines to each other indicates the steepness. So you can see that we start off pretty steep, and then we get into this valley where there's a lot of space between the lines, and it gets pretty flat in that valley. So yeah, that push that you notice comes from the fact that we're starting steep and we're able to travel very quickly across that valley due to starting with a high gradient. Good observation. What else do you see? Yeah.
Yellow, red, and black all have pretty cool ways of getting there. Black, very chill, very calm about it there, but freaks out. And yellow is the same pattern, but it's really fast.
Yeah, so noticing that yellow, blue, and black all seem to take pretty similar paths. I'll give you a hint there, they are based on very similar algorithms, so that is why. And so yeah, both purple and green are momentum-based optimizers, whereas yellow, blue, and black are what are called adaptive learning rate-based optimizers. So this is another one, kind of more zoomed in look. What do you notice about this? About yeah, the paths that these balls take to get to the middle. Yeah, you're noticing that when we get to the bottom of this, it seems like they're bouncing back and forth very quickly. Yeah. From what you, actually, no, I'm not gonna ask that question. Yeah, and again, the momentum-based optimizers seem to get there more smoothly. Okay, so gradient descent, this is our update rule. We compute the gradients, the gradient of the loss with respect to our network parameters, and we apply a gradient update to our weights by letting our new weights equal our old weights minus our learning rate times our gradient. However, there are a couple of problems with gradient descent. First of all, gradient descent implies that we're taking the loss across all of our training data. And so in order to do that, you can imagine that the full gradients with respect of the loss on all of our training data with respect to our weights is going to be too intensive to compute. And then it's also because gradient descent, it basically just travels in the direction of in the direction of the slope. It can easily get stuck in local minima. So we're going to propose a solution to this first problem. We are going to estimate the gradient via a batch. So we're going to sample from our data and do the exact same thing. Take the gradient of the loss on a portion of our data with respect to our network weights, and hope that that sample gradient is going to be a good approximation of the true gradient. So yeah, that allows for smaller, faster updates. So this is our SGD, stochastic gradient descent algorithm. It is exactly the same as normal gradient descent, except we will sample a mini batch of examples from the training set, take the sum of the loss over each of those items, or the average loss, because we're dividing by n, and compute our gradient estimate, and then apply a normal gradient descent update. And then I believe that this just says that in the as we take many stochastic gradient descent updates, we will arrive at the same solution as we will with gradient descent. So there are still problems with stochastic gradient descent. And those involve still getting stuck in those local minima that we were talking about with gradient descent. Oh, another benefit of stochastic gradient descent is that because you're taking different samples over your data set, stochastic gradient descent is better than gradient descent at avoiding those local minima, just by basically adding some more randomness to your gradient signal, which can actually be helpful. But we're going to take advantage of another idea to hopefully avoid local minima even more. That is this idea of momentum. So the intuition behind it is we are going to accumulate velocity of our gradient and use the intuition of kind of a ball rolling down a hill with that gains momentum as it reaches the bottom and continues going in that direction, even if the direction of the gradient changes. So what this looks like is we are going to, actually, you know what? Why don't you take 30 seconds and look through this algorithm and discuss with the person next to you and see if you can figure out how this math maps to the intuition of momentum.
Machine learning. So, okay, so like the target is
delta over the sum of loss based on the loss function. So the gradient, all right, we do the gradient based on that. Velocity
A is
All right, does anyone want to take a shot at explaining the SQE with momentum algorithm? Yeah.
So like normally, or with like just the gradient descent, just had I think zeta, whatever the letter is, times g. And then we were following that negative direction. It's gradient steep is opposite of steep. And so the hyperparameter alpha is the user set that, I guess, the algorithm. That's just kind of how we're going to keep the previous gradient direction, and then we're going to slowly over time, as the do updates, it'll change towards the gradient direction. And also, if velocity is like very high, it has very steep direction, then that will show up as a quick over a long period of time versus like smaller gradient. Velocity is different.
Yeah, that's a great intuition. So yeah, just to recap that, or Michael, did you have a comment as well? Yeah, go for it.
So you should interpret L as the dimension of your surface, then gradient force, right? And then update the velocity to a small change in your force, right? The negative gradient is force. And then continue the velocity of and positions, imaginary bounds in space, right? And vice versa.
Exactly. I think that's a great analogy. So yeah, treating our loss function as or the gradient of our loss as a force that updates the velocity of our gradients. Yeah, and so yeah. So to go through line by line, we have sample many batch of examples. compute the gradient estimate. And then with those gradients, we start with an initial velocity, usually 0. And so the first time we will just have 0 plus our new velocity is 0 plus our learning rate times our gradient. And then at the next step, our next velocity is some weighting function alpha times our previous velocity plus, updated by the learning rate times the gradient. And then our parameter update is our weights plus the velocity. And so that allows, strong gradient signals from earlier to continue on later in training. And so as an example of how this looks, we have an example of a loss surface where it is steepest from the bottom left to the bottom right. And so most of our gradient signal, instead of pushing us towards the minimum, it's actually pushing us back and forth across this very steep valley. You can imagine this as being kind of, like a very narrow bowl. And it turns out that optimizing a very long, narrow bowl is pretty difficult for a lot of optimizers because the gradient signal, the direction in which things are steepest, causes you to basically jump back and forth across the bowl. And actually, in an extreme case, if your learning rate is too large, it can cause you to hop out of the bowl. And what momentum does is it basically cancels out, or it allows us to carry momentum from previous steps. So when the gradient is changing very quickly in one direction and slowly in another, it allows us to take advantage of momentum in that slow direction. But the fact that we have some amount of gradient signal pointing in the long direction of the bowl at every step during training means that momentum in that direction will accumulate over all of those steps across the bowl and eventually take us to the minimum much more quickly. This is a variation on the momentum-based SGD. On the left here, we have SGD with momentum, and on the right, we have SGD with Nesterov momentum. So take a look at those diagrams and see if you can figure out what the difference is between these two. So I'm going to ask you what the difference is and why you think that difference might be useful. Yeah.
It looks like a normal momentum update is purely based on like calculates the gradient from the same spot. While the Nesterov calculates the gradient from where you end up after the momentum, kind of correct back. So in cases where it might be more helpful to look at where it thinks it should keep going, and then so that's kind of essentially like course correct from there instead of just guessing based on where you are now. Kind of take a step forward.
Yeah, I think that's a great example. Was it? Okay. Yeah, I think of this as, this basically prevents you from taking a bad gradient step. If you're hopping, so suppose our momentum is going to carry us across a valley. If we computed the gradient on one side of the valley, it would tell us to normal momentum would tell us to keep on going farther across past the other side of the valley, whereas the Nesterov momentum would look, oh, our momentum is going to carry us across the valley. We'll take our gradient on the other side of the valley, basically softening that that momentum. And I think the intuition of a look-ahead gradient step is a good one. So what that looks like is we apply what we call an interim update, where we update our parameters based on only the velocity, and we get pseudo parameters, which we will call theta tilde. We compute the gradient of the loss at theta tilde, and then we compute a velocity update based on the gradient at that point. And we apply that not to theta tilde, but to our original parameters theta. Okay, any questions on momentum or Nesterov momentum? Yeah.
This one, we say we do the velocity update. That doesn't get applied until the next when we apply the update next.
No, the velocity update gets applied to our weights immediately. So yeah, we apply basically a fake weight update to get a fake gradient, we'll call it, and then we apply our fake gradient to our true velocity to get a new velocity, and then we apply that new velocity to our weights immediately.
And then that new velocity also gets applied to the next loop.
Yeah, so then that new velocity will be used to compute our fake parameter updates. Yeah, question.
So basically, you calculate the gradient 2 times every day.
No. Yeah, so that's a good question. So you compute a parameter update once. The extra computation here is computing an extra parameter update at each step. You good? Okay. Yeah.
So if you start with the velocity,
Let's see. No, so you're thinking, you're employing good adversarial thinking. What happens at step 0? But it turns out that at step 0, what's going to happen is our fake weight update will just be our original weights, and so our gradient will just be our normal gradient. And so the first step is just a normal update, and there's no difference between this algorithm and normal momentum. And then subsequent updates, this becomes something that is, yeah, we will have different pseudo updates. So that's a good thing to point out. What would be the change in memory requirement? Would there be any additional memory required for this algorithm compared to normal momentum? Yeah, what do you think? Twice as much memory? How do you figure? Yeah, that's I'm thinking that's right, because you have to store your original parameters at the same time that you're storing your fake parameter updates, and then you compute the gradient and your velocity. So that's actually another good question: is how many, if M is the memory for one set of weights, how many times M memory would be required for this algorithm? So you said twice, because we need to store weights and weights tilde. But I think we need to store even more than that. We need to store V, weights tilde, V, and weights. Yeah, so that's what I'm getting as well, 4M. Does that make sense?
V and G are the same.
V and G are the size of the parameters because we have the gradient with respect. Yeah. All right, moving on. So yeah, this is just a visualization of how learning rate can affect things. And this is going to motivate our next optimizer algorithm, which is called addigraph. So the problem is that very high learning rates can carry you out of that goal, like I was saying. Low learning rates, you'll never converge fast enough. High learning rates, you'll have the same effect of jumping across the bottom of the bowl. And then a good learning rate ideally will take you all the way to the bottom of the bowl. But some parameters might need to change differently than other parameters at different speeds compared to other parameters in order to be minimized fastest. And so that's our motivation for this next algorithm. We need individual learning rates for each of our parameters. And this algorithm will be our update. So sample mini batch, compute a gradient, and we're going to accumulate the squared gradient. So R starts at 0, and then we're going to accumulate a squared gradient. And you can think of that squared, and this is element-wise multiplication between each gradient values. And then our update will be the original gradient at times basically the inverse of the square root of R. This, you don't need to worry much about delta. Delta is just to make sure you don't divide by 0, and epsilon is our learning rate. So this is exactly the same as gradient descent, except we are dividing by the square root of the sum gradient of the sum of the gradient squares of past learning steps. So let's try to think about why that might be useful. So I'm going to give you some intuition for this. So let's take a couple of example gradient updates. Let's say step 1, it's 1, 1, 1. Step 2, it is 2, 2, 2. Step 3, it is 3, 0, 0. Step 4, it is 5, 0, 0. So basically what this is, what our squared gradient, our summed squared gradient R will be, I'm gonna draw it over here. It will be 3, or no, it will be 1 squared plus 2 squared plus 3 squared plus 5 squared is 4 plus 39. This is R. 39, what will entry 2 be? Oh yeah, I already wrote it out. Whoops. I thought there were 4. Yeah, so our R vector will be 39, 5, 5. And then we're dividing by 1 over square root of R, or we're multiplying by 1 over square root of R. which is going to be about 1/6. And then square root of 2, so 1/2 and 1/2. So let's go back to our narrow bowl example. What you think of as happening here is, and actually let's just ignore the last entry in this. So in dimension 1, we are getting large gradient updates because it is very steep in that direction. Okay. And in dimension 2, we are getting very small gradient updates because the bowl is pretty flat in that direction, right? So what this does is the places where we're getting strong gradients, we are going to reduce the learning rate of those in that direction so that we aren't taking those huge steps across the valley anymore. And we're going to increase the learning rate in the direction where the gradient is not changing quickly. So we're going to shrink it in dimension 1 and increase it in dimension 2. And that will allow us to, again, travel faster in this dimension that's harder to optimize across. Yeah, Spencer. Correct. Yeah. So that is a perfect question. So yeah, the question is, this doesn't take advantage of momentum. Can we combine these in some way? And your answer is we can. And we will show that quickly and end on that. So we'll just quickly skim over this. RMS prop, this basically addresses a problem with AdaGrad where large gradients from the beginning of training influence you too much. And so we use an exponentially weighted moving average so that older gradients have less sway in that AdaGrad algorithm. And that simply looks like this. We just add this row term, which exponentially decays our older R vector. Adam takes advantage of the fact that momentum and AdaGrad are doing different things and combines them into one. So we're going to put momentum terms on both our gradient and our squared gradient. And so we're going to have a update for our velocity, S, and an update for our second moment, R, which we can think of as acceleration of our gradient. And then we update our velocity by basically the momentum of our momentum, the acceleration of our gradient. And that is our parameter update, and we apply that to our weights. And Adam, this adaptive moments optimizer is the most commonly used optimizer used today. It should probably be your default in most cases. But it's just important, although I should just say with the caveat that for Adam, you have to keep track of S and R and your gradients, which means that it's another one of those 4M memory requirements optimizers. So whereas SGD is just 2M. So that's just something to keep in mind. All right. Have a good weekend.